to go ahead for the next talk from Professor Andres Triana from the El Bosque University in Colombia. So we will present the following subject: encoding optical FBG sensors to enhance the capacity of optical sensing systems. Have you the floor, Professor Triana?
Yeah, good morning, good evening to everybody. Thank you. First, I want to thank all the organizing committee for inviting me to give a talk in this research seminar. My name is Andres Triana. I'm with the Universidad del Bosque here in Bogota, Colombia, and this is a collaborative work with my colleagues, Professor Daniel Pastor at Universidad Politécnica de Valencia and Professor Margarita Barón at Universidad Nacional de Colombia. The talk that we are going to give today is called Encoding Optical FBG Sensors to Enhance the Capacity of Optical Sensing Systems. So the agenda for this presentation is first I am going to talk a little bit about what are FBG sensors and why, how we can multiplex, and why are we interested in new multiplexing schemes for these kind of sensors. And then we are going to discuss two approaches, the so-called Amplitude encoded superstructure FBG sensors is the first one, and then the phase and amplitude encoding of superstructure FBG sensors, and finally I'm going to draw some conclusions about the work and the results. So we'll start with a brief introduction. Fiber optical sensors are a topic well known these days. Specifically, fiber Bragg grating sensors were first discovered in the late 70s in the work of Professor Hill that first writes these reflective devices. And it was until the 90s that we can manufacture these devices externally, for example, with this face mask method. And from this point, we have had roughly 30 years of application of these devices as filters in telecommunications, but also as sensors in some academy and industry applications. And the advantages, the main advantages of these sensors are those of the optical fiber. They can transmit information over long distances. They are low weight and size. They are small and light, and they are immune to electromagnetic interference, as we know. So the basic principle of an fiber Bragg grating, as we know it, is basically this is defined as a periodical structure, periodical variation inside the core of the optical fiber that acts as a stop band filter in transmission, as we see here. Basically, each one of these devices reflects back a narrow set of wavelengths around what we call the Bragg wavelength. So the Bragg wavelength, we see here in this equation that the Bragg wavelength, the reflected wavelength, is going to be directly proportional to capital lambda, which is the spacing between these periodical variations inside the optical fiber. So this is the main concept behind these devices used as sensors, because the reflected wavelength is going to be proportional. That means that if we increase capital lambda, if we increase the spacing between this separation between this periodical variation in the optical fiber, we are going to shift our wavelength, and the sensitivity for these sensors is around 1 picometer per microstrain and probably 14 picometers per Celsius degree. Okay, so this is the basic behavior of an FBG device, and Here we have the basic of the interrogation systems. Basically, an interrogation system is a system implemented to detect the reflected signals produced by the multiple sensors in a sensing system. So basically, we have a light source. We have different kind of sources here. But what we are going to do is to illuminate the sensors and capture or detect the reflected signals from each one of these sensors. So as we mentioned before, each fiber Bragg grating sensor is manufactured at a certain wavelength. So WDM is the natural way to multiplex these kind of sensors. Each one of these sensors is going to work at a different wavelength. Nevertheless, we have different interrogation schemes. We have, for example, tunable filters to sweep over the operational range of the sensors. We have, of course, WDM plus TDM multiplexing. We can use low reflective FBGs, OTDR schemes, or interferometric setups to detect these signals from the sensors. But as we said before, all of these systems rely on the very basic nature of these sensors, that is that they are manufactured or they work at different wavelengths. So the natural way to multiplex these kind of sensors is WDM multiplexing, assigning an operational range for each one of the sensors, and usually allowing guard band to prevent overlapping between the sensors. Basically, the limitation on the number of sensors that we can have in a given spectrum is given by this operational range for each sensor, and we do this or we have this limitation because we need to prevent overlapping between two adjacent sensors. When we have two adjacent sensors that are overlapping, the way we detect this is as the summation of the two spectrums, and obviously we cannot detect or we cannot say which central wavelength is from which sensor. So the proposed approach here is intended to encode each sensor with a spectral signature that help to distinguish completely each sensor even under overlapping conditions. If we remember the past figure, we see that in the same operational range of one sensor, we can allocate two or more sensors that if those sensors are designed after a unique shape, or we can say that if these shapes are mutually orthogonal between them. This can be achieved using concepts of CDMA communications, and that's what we are trying to do here. So the first approach is amplitude encoding, in which we use these optical orthogonal codes to shape the amplitude of the sensor. So basically, instead of making one FBG sensor, we construct what we call superstructure FBG sensors, and that those are multiband sensors or multiband devices that are going to be shaped after these optical orthogonal codes. Here in this picture, we see an example of two optical orthogonal codes that basically we define the amplitude of this code word as dictated by the ones and zeros in the code word. The important thing here is that these optical orthogonal codes follow the correlation properties, the autocorrelation and the cross-correlation properties, that states that when we obtain the product between one code word with itself, we are going to obtain an autocorrelation value, an autocorrelation peak value, and when we do the cross product, that means between one code word and another one in the family, we are restrained to cross-correlation values that are not going to reach the value of the autocorrelation peak. That means because that happens because these two code words here are orthogonal between them. So here we have an example of two code words orthogonal, or three orthogonal code words that works the same for these two different families. And as we mentioned before, we are trying to design these multiband devices, these superstructure FBG devices, as dictated by the orthogonal code word. So basically what we want to do here is to construct FBG devices with multiple reflection bands organized after the optical orthogonal code word. And here we have some parameters, some design parameters, such as the spectral width, the reflectivity, or the spectral distance between the subbands, just to mention a few. And the thing here is that obtaining the autocorrelation value for these devices, we are expecting to obtain the central position of this of each one of the sensors, even when these two sensors are working in the same spectral range. So the detection process that we are going to compute here is called the autocorrelation product, as we mentioned before. Basically, we have these formulations to represent this product, but we can see it here in this animation. What we are going to do is the moving product between the total reflected spectrum here in black, and the original shape from each one of the sensors. So we perform this moving product, and by performing this moving product, we are going to obtain when the original sensor coincides with the components of the reflected amplitudes here in the operational range of the sensors, we are going to obtain the autocorrelation value. And for the rest of the positions in the spectrum, we are going to obtain a cross correlation value that, as we say before, this cross correlation value is going to be constrained, limited to, and is not going to reach the autocorrelation value. So after that design, what we do is manufacture these devices. We follow this flow chart here. We part from the spectral design that is what we showed before. Basically, the spectral design is the location of the subbands and the reflectivity of each subbands. Also, we can say what is the width of each one of these subbands. And from this design, from this spectral design, we obtain, we do the synthesis. We use the discrete layer peeling method that is described in this paper. And this synthesis method gives us the complex coupling coefficient that we can see here, and this is what we need to manufacture in these devices. So we see that we have here for these two devices, for example, these spectrums that we see here, we obtain a complex coupling coefficient which has this shape, and we see that the sampling of this synthesis method is roughly 140 microns. That's the separation between each one of these points that we need to manufacture in the device. And we see also that we obtain devices that are 4 centimeters long. So the manufacturing process, the last step is obviously to manufacture these structures inside the core of the optical fiber. To do so, we use the phase mask methods, which basically diffracts the incident laser beam using a phase mask. We see here in this picture the phase mask. We basically have a pitch with basically is a grating that diffracts the first orders of diffraction, the plus and minus first orders of diffraction, creating an interference pattern here in the region near to the phase mask. So this is the region where we are going to put the optical fiber. Here in this picture, we see the setup with the optical fiber here. This is a moving platform that allows us to manufacture each one of these points that we saw before in the coupling coefficient. Here we have a schematic description of this setup. Basically, as we said before, we have an ultraviolet laser that is guided through some mirrors and lenses to the optical fiber, and we have all this in a controlled platform that we can move this fiber each one of the steps that we need, and this is the methods of manufacturing for these kind of sensors. Then we see just a picture that we use a pulse wavelength, a pulse laser beam that is impacting the optical fiber. So after the manufacturing of these devices, we run some experimental validation of these sensors. Basically, what we do here, or what we see in these graphs, is the wavelength, the central wavelength of each one of the sensors in an overlapping scenario. Those scenarios we were performed in a series and parallel setups. Basically, what we can see is that in the same spectral range, we can retrieve the central wavelength of two sensors that are overlapping in the same spectral region. We have here just another example of these experimental results. Here we have in the upper part of this graph, we have the three reflected scenarios here, and the autocorrelation values that point to the central wavelength of each one of the sensors in this merged reflected spectrum. Okay, so we can do this with 2 or 3 sensors. Here we have an overlapping scenario with 3 sensors, for example, and we are able to detect the central position of each one of the sensors. And of course, what we need to do also is to assess the amount of error due to the overlapping that we are introducing in the system. So to do so, we need to differentiate the detection error, the systemic error that is presented in all kind of systems, from the error that is introduced just by the overlapping between the sensors. To do so, we, in the same experiment, analyzed or retrieved the central wavelength of each one of the sensors alone, without the presence of another sensor in the spectral range, and of course with the 2 sensors interacting in the spectral range. And therefore, we obtained the amount of error that we are adding to the system when we introduce these overlapping sensors. We obtain here, for a sensor that is not overlapping, an amount of error, and in this picture we can see clearly 3 regions, and the central region is when the 2 sensors start to overlap. We can see an increment in the error of the system, and we assess this error as low as 3.5 picometers. So this is a very small error. We can remember that the sensitivity of fiber Bragg gratings is of 14 picometers per Celsius degree. So this is a very good result. So another approach that we intended to do is to incorporate more information in the encoding of these superstructure FBG devices. In this case, we try to add information not only in the amplitude of the devices, but also in the phase of these multiband devices. So we use a more robust coding system, and we assign code words for the amplitude and also for the phase of the devices. And here we need to retrieve the amplitude and the phase of the network. So the interrogation system is going to be a little bit different. For the interrogation of these kind of devices, we use a dual wavelength tunable source that is going to be swept over the operational range in such a way that, for example, when the source of the interrogation system is interacting with the sensor here, the two subbands, the two wavelengths of the source match directly with these two subbands, and we see here that we have a pi phase shift between these two subbands. So the retrieve response of this interrogated of these sensors is going to be in amplitudes. We are going to achieve an amplitude value for each one of these cases, but also we are going to have different values for the phase. And what we are going to measure here is the differential phase. So, for example, between these two adjacent subbands, we have a pi phase shift, but for example, between these two, the two last subbands, we are not going to retrieve a phase shift. These two subbands are manufactured with the same or reflects the same phase. So the interrogation approach is differential, and we can see here the same concept. Basically, these are going to be the sensors. The sensors are shaped after these two code words. One code word is used to define the amplitude of the sensor, and the other code word is used to define the phase. So, for example, we have here these values, and what we are going to obtain here is what we call bipolar code word, obtaining positive values. This is the final code word after the interrogation process, and we obtain positive values when two consecutive subbands have the same relative phase, and we obtain negative values of amplitude when two consecutive subbands have a phase shift between them. Okay, so we design three different sensors under this design methodology, and we expect that the autocorrelation values are going to be better than in the past approach. So these are the designing devices. We have the same here in Amplitude. We have just superstructured FBG devices with multiple subbands. And when we obtain what we call the B evaluated response, when we do the interrogation with this dual tunable laser, we obtain this B evaluated response, and we can retrieve the amplitude, the magnitude, and the phase of these components, obtaining clearly the differential phase between consecutive subbands. So in the manufacturing process of these kind of sensors, we are not only interested in the magnitude of this complex coupling coefficient, but we also care about the real and imaginary components of this device. We intended to manufacture these devices, and the result, the manufactured devices, we can see here the comparison between the manufacturer and the design devices, and we see a very good match of these kind of devices in amplitude. And in phase, what we obtain is here we have the design phase shift. We can see here clearly the pi phase shift that we were expecting, and for the real manufactured devices, we obtain the same pi phase shift. Of course, we have some alternating values in between because the dispersive nature of the optical fiber, but we see clearly the difference between these phase shift that we were intended to manufacture. So after that, we implemented the interrogation system. As we said before, basically what we are going to do is interrogate these sensors with a dual wavelength tunable source. We have a tunable laser source that we modulate in single sideband modulation. We obtain these two interrogating signals that are going to be launched to the spectra, to the sensors in the network, and the reflected response of this network is going to be analyzed. It's going to be photodetected here in a vectorial network analyzer, and this photodetected current, the important thing is that it's going to be proportional to the magnitude of the response of the optical network, but also is going to have information about the phase of this network, and that's how we are going to retrieve the position of the sensors. The detection process is the same as we depicted before. Basically, we are computing the correlation product from the total reflected spectrum with each one of the shapes of the sensors. The only thing here is that we take into account not only the amplitude but also the phase of the devices, and we see here experimental results from the detection of an example with 3 sensors, for example, here, and we see that we are able to detect in all the overlapping scenario the central wavelength of the sensors. So we obtain here is the summation of this experiment under an overlapping scenario in the same range of wavelengths. We obtain unequivocally the central wavelength of each sensor, even in complex overlapping scenarios. We perform this experiment, for example, with controlled temperature in the sensors, in each one of the sensors, and we perform the shift in the elongation of the optical fiber. We obtain a good linear fit, and the sensing slope that we obtained was of about 11 picometers. So, as mentioned before, the error due to the overlapping between the sensors was also measured. We obtained for the scenario with 3 overlapping sensors and an additional error of about 4 picometers, which is very good in our expectations. And finally, as the conclusion, what we have proposed with this work was to add a multiplexing dimension. We can say that this multiplexing dimension is the CDM multiplexing scheme, in which we can work also in WDM scenarios, and with this shape of the sensor, with this encoding of the sensors, we can multiply the system capacity 2 times or 3 times, depending on the number of orthogonal sensors that we implement in each operational range. And also the error that we add to the system was always of less than 5 picometers. So I do thank you for your attention. I don't know if we have some time for questions.
Thank you very much. Some questions? Don't have some questions from our speakers.
Sorry, I have a question regarding the presentation. Thank you, Professor Triana. It was a very interesting talk. A question regarding to the interrogation system. You mentioned that you can increase the number of FBG sensors in your fiber. Do we require any specific kind of architecture regarding the interrogation scheme, or is it the classical scheme are using a broadband light source, or do we have to modify this in order to adapt this topology of sensor you are proposing in this talk.
Yeah, thank you. For the first one, for the first approach that we present, that we encode the sensors just in amplitude, we need indeed we can use this scheme with a traditional interrogation system. But in the second approach, this phase and amplitude encoding approach, we need to retrieve not only the amplitudes, which is the natural way that we interrogate FBG sensors, but we need to also retrieve the phase information from the network. So in this second approach, we do need to use a different interrogation scheme that is, as depicted in here. Basically, it's a more complicated way to interrogate the sensing network, because we need to retrieve also the differential phase between the sensors. But it's nothing too complicated. It's just a frequential acquisition of the signal. So for the first case, we can perform it with traditional interrogating schemes, and this second approach needs the information, need to retrieve information from both the magnitude and the phase of the sensing network.
Thank you for your answer. Another comment, Juan?
No, thank you very much. It's clear for me. It's very interesting to see this.
Another question. This question is will serial configurations is dependent on the reflectivity, then how to manage shadowing effect between two or more devices operating at the same wavelength?
Yeah, we need. Thank you for the question. Of course, if we manufacture devices with high reflectivities, we are going to have this shadowing effect between multiple devices working at the same wavelength. But of course, this is a design parameter that we need to have into account. And basically what we do is manufacture these devices at percentage of 40 or 30% reflectivity, so that we can skip these shadowing effects. But yeah, that was considered in the design of the sensors.
So thank you very much for your talk, for your next talk.